Hi everyone! Here we are also asked to solve for this given oblique triangle. When you're asked to solve for the given oblique triangle, that actually means you need to give the measurements of the remaining sides or angles. In this case, we are asked to solve for this side measurement, this angle measurement, and this angle measurement here. In order for us to do that, we could actually use either law of sines or law of cosines. But in order for us to determine which is which, we need to identify what are the given measurements. 7 here corresponds to one side. 12 is also another side. And this angle, which measures 61 degrees, is an included angle of those two sides. This oblique triangle is an example of an SAS oblique triangle. And in solving SAS oblique triangle, we will be using the law of cosines. The law of cosines have different versions of formula, but we can actually pick a specific formula after we are done labeling all of this. If you would like to, we can label this as A, and you can label this as B or side B. We are now left with this remaining side as your side C, which will also tell us that the given angle measurement is angle C. That's the first unknown. We are asked to solve for the measurement of side C. Aside from that, we are to solve for the measurement of these two angles. This is directly opposite your side B, so this is your angle B, and the side directly opposite your, or rather, the angle directly opposite your side A is your angle A. So we are again asked to solve the measurement of angle A and the measurement of angle B as well. Now in solving for measurements of angles, if we already have two angle measurements, let us not use any other formula aside from the triangle angle sum theorem in solving for the remaining angle. This is because we need to make sure that we could retain the 180 degrees so that our figure is really a triangle. It should be no more or no less than 180 degrees. So for this situation, let us try to solve side C first. The formula for the law of sine, one of its version, is by solving C squared, which is the result when we sum the square of A and B, or the given measurements. Then we subtract 2AB with cosine of the given angle C. This has been what is convenient to us because we already labeled the unknown as C. But if we ever use another label, let's say we interchange A and C, we need to really determine the correct structure of the formula. But also, we need to emphasize that we are solving for C, not C squared. So we are going to take the square root of whatever be the value of this entire expression as your radicand. So let's try to substitute all the values here using the given measurements. A is 7, so let's have 7 squared plus B, which is 12. Now that's 12 squared less twice the result of multiplying 7 and 12, and cosine of an angle C, which measures 61 degrees. So we could input all of this at once in your calculators. I purposely picked the scientific calculator in the internet, but since I cannot input them at once, or I could, but it would be complicated, I would like all of you to notice that I will be using first the radicand, or solving the radicand first. I'm going to do it like this: 7 squared plus 12 squared less 2, or let's put parentheses, 2 times 7 times 12 times cosine of 61 degrees. Push equal sign, you will get a result for 111.55, so on and so forth. But this is not yet the correct answer because we need to take the square root of this. So don't forget that if you're going to take the root of a number, it could be either positive or negative, but since C is the measurement of a side, we are sure that to be positive. So let's just simply take the square root of the answer, push equal sign, you will get this result. Let us round it off into 2 decimal places, and since we will be doing that, we will be using approximation instead of an equality. That would be 10.56 or approximately 10.56 units. So you have C is approximately 10.56, and let's use here units because there's no given unit of measurement for the length of side. That's for the first unknown. Let me try to increase the area here for the computation of the two angles. Let's start with the measurement of angle A. We also have a formula for this, which is actually taken from another version of this first formula, and we just simply derive it. But we could also say it like this automatically. It's the inverse or the arc cosine of this expression. Since it's A, that is what you're going to subtract here. So you are left with the sum of B squared and C squared over twice B and C. Notice that we are using C, the already rounded off value earlier. This is also the reason why we stick with this first formula for the first angle, but for the measurement of angle B, we will just be using the triangle angle sum theorem, because if we are going to use the same formula for the measurement of angle B, we might notice later that if we're going to add up all the measurements of angles, it could be less or more than 180 degrees, leaving us with a figure that is not a triangle. So let us try to input this here. Cosine inverse or the arc cosine. B is 12 squared, plus C is 10.56. You take the square of that, less 7 squared, all over twice 12 and product or times 10.56. Close that up. So we have here the measurement of angle A, which is approximately equal to the result of this. Let's try to input the values here in the parentheses first using the same calculator earlier. I'm going to do it like this. Please be guided. I'll be making parentheses to differentiate the numerator and denominator expressions. For the numerator, parentheses, 12 squared plus 10.56 squared less 7 squared. Close it. Then divide with another parenthesis. 2 times 12 times 10. Sorry, that's 10.56. Close it. Push equal sign. This is your result. But we still need to get the result of that when subjected with the cosine inverse. So let's have here our cosine of your answer and push equal sign. You will have this value 35.4282, so on and so forth. We are going to round it off into 2 decimal places, so that would mean approximately 35.43. Again, 35.43. So you have here approximately 35.43, and since it's an angle, we use here degrees. This is what we are going to use for the measurement of angle B. Using the triangle angle sum theorem, we will be subtracting this value and the already given value for the measurement of angle C, which is 61 degrees, from 180 degrees, so that we are already assured that our figure is a triangle. So we will subtract here the already given measurement earlier of 61 degrees, and you have here 35.43 degrees. Since this is already a rounded off value, please do not forget that we will also be using approximation for the result of the measurement of angle B. So the measurement of angle B is approximately equal to, let's subtract that. So you have 180 degrees less 61 less 35.43 degrees. Even if our answer here is an exact value in 2 decimal places, please do not forget that 35.43 is already a rounded off value. Hence, it's not exactly equal to 83.57, but approximately 83.57 degrees. So these are the answers for the unknown measurements of the oblique triangle. We have two angles in one side. Before we end, we have a technique in order for us to determine whether our answers are correct or not. We just simply look at the relationships of the angle measurements and their opposite side, because it should be given that the side directly opposite your largest angle would be your longest side, and the side directly opposite your smallest angle be your shortest side. For angles C, B, and A, the largest angle is this here, 83.57 versus 35.43 versus 61. That would mean this is our largest angle. So B, it should be the side B, which is the longest side, 12 versus 7 versus 10. That's correct. On the other hand, our smallest angle is A. The measurement of angle A is 35.43 as versus the two other measurements. So we would know that A, which is 7, is the shortest side of this SAS oblique triangle. 7 versus 12 versus 10. That's a hint that you could use in your future computation. This is how we solve the given SAS oblique triangle.